Hello everyone, so this is our question session 3. We will start with the last question we left in our session 2. So this is the question. A fluid is confined in a cylinder by a spring loaded frictionless piston. Okay, so the pressure in the fluid is linear function of the volume. Pressure in the fluid is linear function of volume. Okay, internal energy is given by this equation, and we have been given with the states P1 V1 and P2 V2, and we have to calculate heat and work transfer. So in last lecture I told you that if uh, if the piston is spring loaded and it is linear, so we should to calculate work we should directly use PV diagram. Okay, so in this question we will draw PV diagram, PV, and we will mark both P1 and V1 points. So let's say this is 170 kilopascal and 0.03 meter cube, and since the pressure it is mentioned that the pressure in the fluid is linear function of the volume, so we will consider it to be linear function of the volume and get our pressure, and this is 0.1, this is 0.2, pressure of 400. Okay, and volume of 0.06. So the work done can be obtained by the area under the curve. Okay, and this area value will be half into sum of parallel, since this is trapezoid. So then area of trapezoid is half into sum of parallel sides. Sum of parallel sides is 170 plus 400 into height. Height is 0.06 minus 0.03. Okay, so we will calculate this value. 570 into 0.03 to work done, we obtain work done is equal to 8.55 kilojoule. Okay, and next we have to calculate the amount of heat transfer. Okay, so to calculate heat transfer we can directly use first law of thermodynamics, which delta Q is equal to delta U plus delta W. Okay, now, or we can directly write it as like this: Q is equal to delta U plus W. So we have to calculate Q, and we know delta U we can calculate as delta U is equal to U2 minus U1, and we have been given with the expressions of U, so we can get it. U2 minus U1 is 3.15. Now U2 is P2 V2 minus P1 V1. Okay, so we can calculate that delta U is equal to, so when we substitute the values, 400.06 minus 170 into 0.03, okay, 18.9, and this into 3.15, we get the value of delta U as 59.535. This is in kilojoule, so we can get Q as 59.535 plus 8.55, so we get Q is equal to plus 8.55, Q is equal to 68.085. okay, this is in kilojoule. So this is the solution for this question, and now we will move to next question. This is the next question. Okay, so it is given that the given figure shows the variation of force in an elementary system which undergoes a process during the plunger position changes 0 meter to 3 meter if the internal energy of the system in the end of the process is internal energy of the system at the end of, so it means that internal energy of the system at the end of process is 2500 joule higher. It means that delta U is given as 2500 joule, which is like u2 minus u1. It is given if final is higher than initial, so we can directly consider it positive 2500 joule. Then what will the heat absorbed during the process? Okay, so we have to calculate the heat absorbed. For heat absorption, we can use first law of thermodynamics. We indicate Q is equal to delta U plus W, and for this we have to calculate the work done through this process. Okay, so we know that work done is equal to force into displacement. So basically, if we calculate the area of this overall curve, so we can calculate what is the value of work done. So we calculate the area, half into base into height. Base is like this is 1 meter and height is 5 kilonewton plus total area of rectangle. Like first we have considered this triangle, okay, and then we have considered this rectangle. Okay, so this rectangle value is 5 into 3 is equal to 2.5 plus 15 is equal to 17.5. This will be in kilojoule, since the unit is kilonewton and this is meter. So we have obtained the work done as 17.5 kilojoule. So we can obtain our Q is equal to, so delta U is given in like this is 2500 joules, so we can write it as 2.5 kilojoule. So we can write 2.5 plus 17.5 is equal to 20 kilojoule. So this is our solution for this question. Now we will move to next question, which is from the chapter first law of thermodynamics. Now we will discuss the first question number 1 of first law of thermodynamics. Consider an ideal gas in a frictionless piston cylinder assembly. The weightless piston is weightless, is initially loaded with large number of small weights. How would you carry out the reversible isothermal expansion process? Reversible isothermal expansion process. So for the reversible isothermal is also known as quasi-static. For isothermal it should be quasi-static, and for the reversible also, okay, quasi-static, reversible. Assume a large number of very small weights and an arrangement for reversible heat transfer are available. So let's say this is our system and we have a piston installed in the cylinder. Let's say that as it is mentioned, there are few blocks, small blocks. So we will just do it the block. Okay, so if we have to make it expansion, there should be expansion. So for expansion we should provide some heat to it first. Okay, so we should provide some heat and we should start removing blocks one by one. Okay, we should start removing the blocks one by one. So without adding or removing the weight, adding weight on the piston and transferring heat to the system. Okay, so option D is correct here. Next we will be moving to question number 2. Consider a steady flow of the air. CP this in adiabatic passage. The air enters the passage at 100 kilopascal 500 Kelvin at a velocity of 150 meter per second and exit the passage at Kelvin. To be ideal gas, neglect the gravitational passive effect. Okay, now since we have been given that the air enters a passage, let's say this is the passage and this is condition 1, that is 100 kilopascal, okay, 500 Kelvin, this is T1, this is P1, and similarly we have been given with velocity 150 meter per second, which we can be used as C1. Okay, next what is given, it is given that exit the passage at location 2 with temperature T2 is equal to 510 Kelvin. Okay, assume air as an ideal gas and neglect gravitational effect in the passage. So we can directly use steady flow energy equation here to calculate the exit velocity. So let's say what is the steady, let's first write steady state energy flow, steady flow energy equation. H1 plus C1 square by 2 plus GZ1 plus Q is equal to H2 plus C2 square by 2 plus GZ2 plus W. Okay, now we can see here there is no potential, no heat transferred. Okay, no potential, no work transfer, so we can get H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. Okay, now this value of H can be calculated by using CPT. Okay, so we can write, since we have to calculate C2 square, C2, so we can write C2 square by 2 is equal to, now just remember one thing, the value of H is given in, like when we will calculate, we will use H is equal to Cp into T, and Cp is given in kilojoule per kg Kelvin. So we will receive the value of H in kilojoule, but when we when we will do C square by 2, this will be in joule. Okay, joule per kg, so we will divide it by 1000. Okay, so C2 square by 2000, and in generally in what happens, what we do, we will divide this whole term by okay, let me do it again, divide whole by term by 1000, C1 square by Z1. Similarly we will divide C2 square by 1000. Okay, so this is generally what you call what we use mathematically for our steady flow energy equation. Okay, so we will do the same thing here. Easy. So C2 square by 2000 will be equal to H1 minus H2 plus C1 square by 2. So from here we will get Cp into T1 minus T2 plus C1 is value is 150 square by 2000. Okay, so T1 minus T2 is minus 10, 500 minus 510, so we have to do 150 square divided by 2000 minus Cp value is 1.005 into temperature difference is 10. Okay, so we get C2 square by 2000 is equal to 1.2, and we will multiply by 2000, then we'll take a square root, so we get C2 is equal to 48.98 or 48.99 meter per second. So we get answer 49 meter per second, and only this option is available, so it will be the correct option. Okay, okay, so you can see that since the velocity is decreasing in general, if the if it is flow is okay, so let's talk about this topic later. So let's just consider here that is, since the velocity is less than the inlet velocity, so you will get a diffuser. So this will be a diffuser. Okay, next question number 3. Air at a flow rate of 1 kg per second enters the nozzle of an jet engine at a temperature of 1800 Kelvin, pressure of 200 kilopascal, and velocity of, so we have been given that enters a nozzle. So let's say this is a nozzle. Okay, so we have been given m dot is equal to 1 kg per second, given T1 is equal to 800 Kelvin, given P1 is equal to 200 kilopascal, C1 is equal to 50 meter per second, it leaves the nozzle at a temperature T2 is equal to 650 Kelvin and pressure P2 is equal to 100 kilopascal, and heat loss at a constant rate. So it is given that the heat loss to surrounding is 25 kilowatt. Okay, so assume the air to behave as an ideal gas. Cp, we have given Cp value is 1.005. Neglect the potential energy change, the exit velocity of the air. So again we will apply steady flow energy equation. H1 plus C1 square by 2000 plus GZ1 by 1000. Since we have been told to neglect, or we can just write it, we can read plus Q is equal to, and notice one thing, is equal to, since there is mass flow rate E1, we can directly write it as like, okay, we can do it as like Q dot capital Q divided by M dot, okay, is equal to H2 plus C2 square by 2000 plus GZ2 up by 1000 plus W by M dot. Now here we will neglect the potential energy losses. There is no work output, so we will write this. You can write this equation as H1 plus C1 square by 2000 plus Q, let's say this is value of Q, by M dot, okay, is equal to H2 plus C2 square by 2000. Okay, what we will do now, we will substitute all the values here. So for like we have been provided with temperatures, so for H we will do Cp T1 minus T2 plus, okay, so let me write it here, Cp into T1 minus T2 is 800 minus 650 plus C1 square is 50 square by 2000 plus Q by M is 25 by M is 1, okay, is equal to C2 square by 2000. So we will calculate all the values. 800 minus 650 is 150 into 1.005 Cp, and then we will add 50 square divided by 2000, okay. Now we will add in this 25, we got 177, okay. Now we will multiply it with 2000 and then take a square root, so we would get, from here we will get C2 is equal to 595 meter per second. Option D is correct. Okay, now moving to next question. It is mentioned that if delta Q is the heat transfer to the system and delta W is the work done by the system, then which of the following is an exact differential? Okay, so we have discussed it in last lecture, or last to last lecture, in first law of thermodynamics, that when we define that energy is a property in the consequences of first law of thermodynamics. So first law of thermodynamics indicate delta Q is equal to du plus, or dE plus dW. From here we can write dE is equal to delta Q minus delta W. Since E is a property, okay, property, so we can write that hence delta Q minus delta W is also a property. So that is a point function. Since delta is a point function, so this will be also a point function, and since it is a point function, it will be exact differential. Okay, so answer is D. Next we will be moving to question number 5. Air enters the adiabatic nozzle as at 400 kilopascal and 900 Kelvin with negligible velocity. So we have been given the nozzle is adiabatic. Since nozzle is adiabatic, Q is equal to 0. Okay, so we get T1 is equal to 900 Kelvin and C1 is equal to 0. Negligible velocity it is mentioned. The flow of ideal gas exit pressure is 100 kilopascal. The exit temperature Kelvin at the exit. Okay, so it is asked about the exit temperature in Kelvin and exit velocity. What will be the T2 value and what will be C2? Okay. So since in this question it is mentioned that this adiabatic nozzle, so we can assume that the process is adiabatic, that is isentropic process. The process is isentropic. So we can directly use the relation T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma, and consider since it's given A, so gamma will be 1.4 and P2 exit pressure is 100 and entry pressure is 400. This will be 100 by 400 times power 1.4 minus 1 by 1.4. Okay, so when we calculate the value, we will get, like T1 is given as 900, so we will get T2 is equal to 516.87 Kelvin. Okay, this is our temperature. And we can now use steady flow energy equation. So it will be reduced in form of H1 plus C1 square by 2000 plus Q, so Q is 0 instead of it is adiabatic, and we will get H2 plus C2 square by 2000. Since C1 is negligible, so this term will be 0, and hence we can get C2 square by 2000 is equal to Cp into T1 minus T2. Okay, so once we calculate this, we will get from here, when we substitute all the value, we will get C2 value to be 877.5 meter per second. Okay, so this is our answer, and option C is correct for this. Next, the first law of thermodynamics is valid for all processes, only reversible processes, only cyclic processes get carried reversibly. No, all processes. First law of thermodynamics is valid for all type of processes. Okay, I told you in the last class. Okay, next, mass flow rate of the air in a compressor is 1 kg per second. So there is a compressor, it is mentioned as a compressor. So let's make a compressor. This is a compressor. So it is mentioned that mass flow rate is 1 kg per second. The inlet conditions, let's say this is the inlet, okay, and this is the outlet. So it is given as P1 is equal to 0.1 megapascal, T1 is equal to 300 Kelvin, and at exit pressure P2 is equal to 1 megapascal, and temperature, okay, assuming the compression process to be adiabatic and reversible, air to be ideal gas, the power input to the compressor is, okay. So we have to first find T2. So since the process is given to be adiabatic, we can directly use T2 by T1 is equal to P2 by P1 की power gamma minus 1 gamma. So from this P2 by P1 we will get 10 की power 1.4 minus 1 upon 1.4. Okay, so let me calculate the value. We will get 10 की power divided by 14. Okay, so this value will come out to be 1.93, and when we multiply the value of T1, that is 300, we get T2 is equal to 579.2 Kelvin. Okay, and since we have to calculate power, so we can calculate compressor power by using steady flow energy equation. We will get the equation H1 plus, since there is no enough given, H1 plus Q is equal to H2 plus W, and since Q is 0 in the nozzle adiabatic, so we will get W is equal to H1 minus H2. So okay, so this value will be negative because the compressor work is always negative. But to obtain the positive value, we have to do H2 minus H1. Use 5, we will obtain the value of W is equal to 280.6 kilojoule. So option C is correct. Sorry, kilowatt, kilojoule. And to obtain work, we have to multiply with mass flow rate, and we will get 280.6 kilowatt. Okay, next question is, steam turbine is used to produce work at the thermal power plant. That what type of work it is? So this is shaft work. At steam turbine we obtain shaft work. Okay, next, when 1 kg of ideal gas expands reversibly and adiabatically in a piston cylinder element from a initial state of P1 V1 T1 to in final state of P2 V2 T2, the work done by the gas is. Okay, so we have been asked to calculate the work done on the gas when it is expanded adiabatically. Okay, so reversible and adiabatic. So for this case, reversible and adiabatic case, we get our work done is given by P1 V1 minus P2 V2 by gamma minus 1, and we can write P1 V1 to be mR T1 minus T2 by gamma minus 1, but we can also write R upon gamma minus into is equal to CV. Okay, CV into T1 minus T2. Since it is given as 1 kg, so we can put M is equal to 1, and we will obtain CV into T1 minus T2. Option C is correct. Okay, next question 10. A balloon contains an ideal gas is initially kept in an evacuated and insulated room. Balloon contains initially kept in evacuated and insulated room. The balloon ruptures and gas fills the entire room. Which of the following statement is true at end of the process, above process? So it is mentioned that containing the ideal gas kept initially in, so this is insulated, and here it is vacuum. Okay, and it is mentioned that a balloon is ideal gas kept. Okay, now it ruptures. Okay, the internal energy of the gas decreases from its initial value, but the enthalpy remains constant. Both internal energy and the enthalpy of the gas remains constant. Both internal energy and enthalpy of the gas remains constant. The internal energy gas remains increases. The enthalpy remains constant. Both internal energy and enthalpy of the gas increases. So it is mentioned that a balloon containing the ideal gas is initially kept in an evacuated and insulated room. The balloon ruptures and the gas fills the entire room. Okay, so what we can say here, balloon ruptures, the pressure is reduced, but the volume is increasing. So in this question it is mentioned that the room is vacuumed and insulated, and the board ruptures. So you can see that this is a case of free expansion. Okay, free expansion. What happens in free expansion? Free expansion, uh, we can say that in free expansion there is no work done and there is no heat transfer. Okay, and I mean in free expansion, we say that the energy, since there is no heat transfer and work transfer, from first law we get du is equal to 0. It means that u1 is equal to u2, and for ideal gas we can say is equal to T1 is equal to T2. And since T1 is equal to T2, for ideal gas, in this condition u1 is equal to u2 and h1 is equal to h2. So option C is correct. Okay, now we will be moving to next question. During the process with heat and work interaction, the internal energy of the system increases by 30 kilojoule. Okay, internal energy of the system increases, so delta V will be positive 30 kilojoule. The amount of heat and work interaction respectively. Okay, so the simple question. So from first law we can write Q is equal to delta U plus W. Okay, now we can write delta U is equal to Q minus W. So we have to check all the options such that if we subtract Q minus W, we should get 30. Okay, so let's say this is heat and work. So these are values for Q and these are values for W. We have to do Q minus W. So this won't be, and if we do this question Q minus W, we will get correct answer. Okay, so we get the answer B. Now next question. And the internal energy of the certain system is a function of temperature alone and is given by is equal to this. Okay, the system executes a process for which the work done by it per degree temperature increases. Okay, work done by it per degree temperature increase is this d by dt is equal to Q minus W, the heat reaction per degree temperature. Okay, so it is given that there is certain system. Okay, and for this system we provide some energy. Internal energy of the system is given, not provide some energy. So this internal energy of the system, this internal energy U is given by 25 plus 0.25 T. Okay, and it is mentioned that if the system execute a process in which the work is done by it per degree increase is okay, per degree temperature increase. Okay, if we increase the temperature by 1 degree, we get the work of 0.75 kilonewton per meter for 1 degree raise in temperature. Okay, now it is asked that the heat rejection per degree. What is the heat reaction per degree? Okay, now so see, there is the equation given, d by dt is equal to, then must be q dot and minus w dot. Okay, this from first equation we have differentiated it with respect to t, so we can so let's write it as e also. So we get that it is mentioned, so temperature total work per degree, so dw by dt is given as 0.75, so we can write d by dt is as 0.25 is equal to q dot we have to find minus w dot we known as 0.75. From here we can get q dot is equal to 1 kilojoule, okay, per second, or not per second, this is not with respect to time, this is with respect to temperature, so per degree Celsius. So we can say answer to be D1. Okay, now moving to next question, question number 13. 170 kg of heat is supplied to a system at a constant volume. Okay, then the system rejects 180 kilojoule of heat is supplied to system at constant volume. The system rejects 180 kilojoule of heat at a constant pressure, and 40 kilojoule of work is done. Okay, if the system is finally brought to the original state by adiabatic process, initial value of internal energy is 10, then which of the following statement is correct? So we said that we have initially at location 1 we have U1 is equal to 100 kilojoule. Now for process 2 at point from process 1 to 2, what happens from process 1 to 2? We have supplied Q1 at Q at constant volume that amounts to be 180 kilojoule. Okay, now 170 kilojoule. Now after that we have done 2 to 3 supplied to the system at 170, and next we have the system rejects heat at the rate of 180 kilojoule. The system rejects 180 of heat at constant pressure and 40 kilojoule of work is done on it. And in the same we have done the work and 40 is the work done on it, so work done must be minus 40 also. Okay, next it is mentioned that if initial value of internal energy is 100, then the system is finally brought to the original state by adiabatic process. Okay, from 3 to 1 it is adiabatic, it is mentioned adiabatic. Okay, so it is mentioned that 1 to 2 at constant volume. Since there is constant volume, so it means that work done is equal to 0. So from here in all these processes we will use Q is equal to delta U plus W. Okay, the first law of thermodynamics. So in this case you will put Q is equal to 170, then W is equal to 0. So you will get U2 minus U1 is equal to 170. You have given the value of U1 is equal to 100. So you will obtain value of U2 is equal to 270. Okay, now for this particular case you have been given Q is equal to minus 180 and work is equal to minus 40. So you will get delta U is equal to minus 140. Okay, minus 140 U2 minus U1, or U3 minus U2, but you have to go to U2 to be 270. So you will take it to another side and you got 270 minus 140. So U3 is equal to 270 minus 140, 130. Okay, next for adiabatic we know that Q is equal to 0. Okay, so we can directly get work done from this, because U1 we know that U1 is equal to 100 is already given. Or let's see first on options first. The highest value of internal energy occurs at the end of the constant volume process. Yeah, exactly, it is correct. The highest value of internal energy is 270, which occurs at the end of constant volume process. The highest value of internal energy occurs at the end of constant pressure. No. The highest value of internal energy occurs after adiabatic expansion. No. The internal energy is equal to it. Okay, so option A is correct here. Okay, next we'll moving to question number 14. Question number 14 is a fluid flowing along a pipeline undergoes a throttling process from 10 bar to 1 bar in passing through a partial open valve. Before throttling, the specific volume of the fluid is this, and after throttling it is this. What is the change in specific internal energy during throttling process? Okay, so we know that for throttling our H1 is equal to H2. We know H1 is equal to H2. Okay, Now what we can do here, since the process is throttling, h1 is equal to h2, and we can further write h is equal to u plus pv, so u1 plus p1 v1 is equal to ut plus p2 v2. But we can see, in question it is asked the change in specific internal energy. Change in specific internal energy will be u2 minus u1. You have to calculate u2 minus u1. So rearranging, we will get p1 v1 minus p2 v2. Okay, now we can substitute the given values here. Value of p1 is, if we substitute it in, let's convert it in kilopascal. So 10 bar is p1, so 10 bar will be 1000 kilopascal into volume will be, before throttling is 0.5. okay, minus 1 bar will be 100 kilopascal into volume is 2 meter cube per kg, so we will get change in internal energy to be 300 kilojoule per kg. Okay, so option D is correct. Next we will move to question number 15. When an ideal gas gamma 7.7/5 is heated at a constant pressure, the fraction of heat energy supplied which increases the internal energy of the gas is, okay, heated at constant pressure. Okay, so it is heated at a constant pressure. The fraction of heat energy supplied which increases. Okay, so it is as I told you earlier that Cp is always greater than Cv. And why is that? Because Cp carries both responsibility of increasing internal energy plus work done. Okay, so it is asked what fraction of heat energy supplied which increases the internal energy of the gas. Okay, so we know Cp by Cv is equal to gamma, and since it is asking about Cv is equal to Cp upon gamma. Okay, no, sorry, so it is asking about now in question it is asked what fraction of heat energy supplied increase the internal energy of the gas. So let's say change in internal energy upon total heat supplied, we have to calculate this ratio. Okay, so change in internal energy will be mcv dt, cv delta t, and change in and total heat supplied will be cp delta t. So we have to our answer will be cv by cp, that will be 5/7. Okay, option D is correct. Next we will be moving to question number 16. In question number 16 it is asked two cylinder A and B fitted with piston. Cylinder contains equal amount of ideal gas. Okay, at 300 Kelvin the piston A is free to move while piston is held fixed. The same amount of heat is supplied to gas in each of the cylinder. The reason temperature of the gas in case A is 30 degrees. Okay, so it is mentioned that there are two piston cylinder arrangements. Okay, let me draw piston cylinder arrangement first. So this is the piston cylinder arrangement. Okay, there are two piston cylinder arrangement. Okay, let me copy and then I will just paste it here. It is mentioned that in first case, in case A, and this is case B, what is happening? Equal amount of both having both having temperature equal amount and 300 Kelvin both at. Okay, the piston is free to move. Okay, so piston is free to move, and in piston B there is a stopper there, so B is fixed. Okay, so it is fixed. Okay, now the same amount of heat is given to the gas. It is given amount Q, it is also given around Q. Okay, now what happens that the temperature increases. इसके लिए हमारा डेल्टा टी is given that delta TA is equal to 30 Kelvin. Okay, now we can see from here that q, this q at A is equal to Cp dt. Okay, mcp dt, mcp to delta T of A, and this same amount is provided by QB, which will be equal to mcv delta TV will be equal to QB. Okay, so we can cross the both m values, so we will get Cp by Cv times of delta Ta is equal to delta Tv, which will be equal to 42 Kelvin. Okay, this is the answer. Next, question 17. It is given that in the given process the ideal gas delta W is equal to 0 and delta Q is negative. Then okay, so we can directly do it using the first law of thermodynamics. Delta Q is equal to du plus delta W. Okay, so it is given that delta W is 0 and delta Q is negative. Okay, so it means that du is less than 0. Okay, it means that temperature is decreasing, temperature will decrease. Okay, option A is correct. Next, in question number 18, it is mentioned that an ideal gas taken through the cycle A B C A, as shown in the figure, is the net heat supplied to the cycle is equal to 5 kilojoule. Okay, net heat supplied is 5 kilojoule. Then the work done by the gas on the process. Okay, we can directly use first law of thermodynamics. Q is equal to delta U plus W. So Q is 5. We know that delta U for a cycle is 0 plus W. So we get W is equal to 5 kilojoule. Supplied to the gas in the cycle is 5 kilojoule. Okay, so this work done is the work done by the gas in the cycle, in the process CA. Okay, sorry about that. This is the work done in cycle. Okay, this is work done in cycle. If we talk about specifically for the process, so let me think about a bit. Okay, so see here, this area is work done by cycle. Okay, this is work done in cycle. Now if we have to this, what is this area? This area is work done by gas in the process CA. ये हमारा ये area है. Okay, so if we have to calculate this area, so work done by CA is equal to total area, like work done by AB. Okay, or else we can see that work done by cycle is equal to work done by AB plus work done by BC plus work done by CA. We can directly omit this thing. We can use this formula. So work done in cycle is 5. Work done in AB, since in the expansion the work done will be positive and value will be 10 into 1, that is 10, plus in BC, since it is a constant volume process, the work done will be 0, and in CA we have to calculate work done in CA. So from this we can get work done in CA is equal to minus 5 kilojoule. Okay, option A. Next, moving to question number 9. An ideal gas undergoes cycle process JKLM with respect to cycle. Okay, we have to match the following. Okay, so let's do it. We can see here that process JK is a constant volume process, and in constant volume process work done is 0. We can match A with JK, work done is 0, 2. Okay, 2, and for any other option we'll see what happens with q. Okay, but there is no option available for a to be 2, so we have to see what with the value of q. Okay, since it is a compression cycle, so it's not a compression cycle. The pressure decreases at a constant volume. This is not a compression. So okay, let's see for jk. For jk cycle, work done is equal to 0. Okay, so q is equal to delta u. Now the question is, what is the value of delta u? Okay, so from j to k our pressure is decreasing but volume is constant. Okay, so pressure is directly proportional to temperature. Okay, pressure directly proportional to temperature. It means, और ये क्यों है? क्योंकि हमारा वॉल्यूम इज इक्वल टू कांस्टेंट है. Okay, since volume is constant, pressure is directly proportional to temperature, and at k and from j to k the pressure is dropping, so temperature will also be dropping. Temperature dropping, this means that delta u is less than 0, negative, so q should be negative. So for a we should get option 3, b, k to l. K to l is constant pressure and expansion, so work done will be positive. In k to l, work done is equal to work done will be greater than 0. And what else? What else will happen? At constant pressure the volume is increasing, so the volume is directly proportional to T because of pressure is equal to constant, and due to this we get delta U is greater than 0. Okay, volume is increasing, so pressure will be, delta U will also be increasing. So we cannot tell anything about delta Q. Okay. Okay, why not? Let's stay this put. For L to M, the work done will be 0. So we don't know about B, but for C, work done is definitely 0. Question number 2. 3 2. It is also available in one option. Let's check for MJ. For MJ process, okay, from these two options only, from A and C we get the correct option. So we will move to next question. Okay, so in this question it is mentioned that water in a container. Okay, so water in a container at a volume of 2 liter. So this is our 2 liter water. Okay, now the lid of container is open. It is mentioned that lid is open, and the coil is placed. Coil value is 1 kilowatt, and the energy loss at the rate of 160 joule per second. In how much time the temperature will raise from 27 degrees Celsius initial temperature T1 is equal to 27 degrees Celsius, final temperature T2 should be 77 degrees Celsius. Okay, now Cp for water is given as 4.2 Cp, or we can directly say C, kilojoule per kg Kelvin. Okay, so we will apply the conservation of energy here. So we will say energy inlet is equal to energy output plus energy stored. Okay, so how much amount of energy provided? 1 kilowatt energy. I mean, we can write it in 1 kilowatt into 4 times T. We have supplied this energy. Okay, and how much energy is stored? Stored energy is mc delta T. Okay, so now mass of water is rho density into volume. Density of water is 1000. Okay, into volume is 2 liter. 2 liter means 2 liter is mentioned at 2 into 10 to the power minus 3 meter cube. Okay, So 2 liter will be 0.002 meter cube. Okay, rho into V mass into Cp. Cp is given as 4.2. Okay, into delta T. Delta T is given by T2 minus T1 is equal to 50 into 50. So this is the energy stored. Okay, plus energy release energy amount is 160 into T divided by 1000. Why is 1000? To convert it in kilojoule. Okay, now this is the question outlet which is created. Now we can directly calculate the value of T from here. Okay, so let me do it. On solving this, we get T is equal to 500 seconds. We can further reduce it in minutes by dividing it to 500 divided by 60. So we get 8 minutes and 20 seconds. Okay, so option A is correct here. Now let's move to the next question. Question number 21. Okay, so a fully charged car battery gradually discharges while lying on the shelf at a constant temperature. Okay, during the discharging it loses 250 kilocalorie to the environment. The battery is then recharged slowly to the initial state. The charging process consumes 0.53 kilowatt hour of electricity. What is the energy transfer during the charging process? Okay, so let's do it. Kilocalorie. So let's first draw a battery. So let's say this is the battery. This is the battery. So it is mentioned that the battery loses the heat at a constant rate. Q discharge is equal to, we can mention it in negative terms because it is a loss, minus 250 kilocal. We can multiply it with 4.2 to convert it in kilojoule, or to be more exact 4.184. okay, so we will get Q discharge at minus 1046 kilojoule. Okay, and now the another mentioned that is Q supplied to charging, work done is supplied. The Q W charge we have been provided with 0.53 kilowatt hour. We can multiply it by 53 into 3600 kilojoule. Okay, so this will be give out to be 1908 kilojoule. Okay, now we can apply energy balance. How do we apply energy balance? So let's we can use the first law of thermodynamics. First law of thermodynamics gives us Q is equal to delta U plus W, but since it is a cyclic process, there is charging and then discharging, then there is again charging, so delta U for the complete process will be 0. So you can see that the net Q is equal to W we can obtain here. Okay, so let's see what is the total Q. So we can write it as summation Q is equal to summation W. Let's say now there is two type of heat here. So we have been asked what is the heat transfer during the process. So during the charging there will be some heat during the charging that will be provided. Okay, so we can write Q is equal to Q charge plus Q discharge. Okay, but there is only one type of work, that is q charge. During discharging it isn't providing any type of work, or it isn't mentioned in the question, so we will consider it to be 0. And q charge we have to calculate, q charge we have to calculate, plus q discharge we have been provided with the value of q discharge 1046 is equal to, and q charge we have the value of q charge to be, sorry, w charge to be 1908. So, and one more thing for you to mention, since this the work charge is provided, so this should also be negative. Okay, we will get minus 1908 here, and on solving we get q charge is equal to minus 862 kilojoule. So this will be the answer. Okay, next we will be moving to question number 22. In question number 22, it is mentioned that first law of thermodynamics applies to variable process. 1 to negligible kinetic potential energy change is given by the expression. Okay, so it is asking about our energy conservation equation in case of unsteady flow. Okay, so in unsteady flow we have obtained the equation. What was the equation? Equation was du by dt is equal to m dot hi plus q minus m dot he plus w. Okay, so this was our energy conservation equation. We can deduce from it from here that u can be written as mu. Okay, so, and all the terms, sorry, this shouldn't be here, it shouldn't be like this, it should be like dm by dt. Okay, so this option should be correct one here. Okay, because there is a mass flow rate, rate of mass flow rate, and rate of heat, and rate of work. Okay, option C is correct. Next we move to question number 23. A closed thermodynamic system undergoes an unsteady process. Work is done on the system. Okay, closed undergoes an unsteady process. Okay, work is done on the system, at an average rate of, so work is done on the system at average rate of work is minus 260 watt. Okay, minus 260 watt. Okay, and the heat is lost to the surrounding. Since heat is lost, we have to also consider it to be negative 10 watt. Neglect change in kinetic potential energy of the system. The change in internal energy during 1 hour. 1 hour change in internal energy. So you can we can consider du by dt is equal to m dot I hi plus q minus m dot he plus w. Since it is mentioned that the system is closed to thermodynamic system, so we can consider there is no inlet and outlet outflow, so we can directly get du by dt is equal to q minus w, and from here q minus w value will be q minus w, it will be 250. And in 1 hour, if we have to calculate the value in 1 hour, so this will be in watt. Okay, in 1 hour delta u will be 250 into 3600 joules. Okay, so we can calculate it in terms of 900, we will get 900 kilojoule. Okay, so since this term is positive, so it means that the internal energy increases by 900 kilojoule. Okay, next we will move to question number 24. A gas is released from a pressure cylinder by opening a valve suddenly. Okay, assume kinetic potential energy changes negligible, and cylinder is perfectly insulated. MHU are mass, specific enthalpies, and specific internal energy of the gas in the cylinder are in the cylinder. Okay, and at respectively mass at exit, specific internal energy. Okay, so it is mentioned that there is a pressurized cylinder. Okay, the pressurized cylinder, and suddenly a valve is, let's say that it is like this. So it is said the valve is suddenly opened, so the gas will be released from this. Okay, discharge is at m is exiting from here, and in interior it is mhu, and then at exit it is m exit, u exit, and h exit. Okay, so mass flow rate specific to which the following represent the transient process of a gas. Okay, so we can directly use the conservation of energy. Conservation of energy is from that we get equation du by dt is equal to m dot h1 plus q minus hi, sorry, m dot h e m dot e I plus w. Okay, so this is the standard equation which is generally used. So here also we can see that since there is no entry, so here since there is no entry mass, we can directly term it as 0, and it is also mentioned to be perfectly insulated, so q is also 0. Okay, now only term we have been left with are m dot e he plus work done, and since there is no work, so this can also be termed as 0. So we will obtain from here uh, m dot e he is equal to minus d, this is m into u by dt. Okay, so we will get h exit, so this is the equation we get. Okay, so now we will move to the next question. Tank contains 9 kg of liquid water at an initial temperature T0 degree Celsius. Okay, a coil removes heat at the rate of K1T from the tank. Okay, let's first make a tank. So this is tank, 9 kg water. Okay, now what we have done, we have installed a cooling coil, and from cooling coil we are removing heat at the rate of K1 T, initial temperature of, so T1 initial was T0 degree Celsius, and a pedal wheel by constantly steering maintain the uniform temperature. Okay, so there is also a pedal wheel that is arranged, and with its help we infuse the amount of work W. Okay, the rate of, and its value is K2 T. Okay, so but since both are like work is heat is exiting, so this will be negative, work is input, so this is will be negative. The temperature T in degree Celsius and Q1 and Q2 constant. The rate of internal change energy inside the tank will be balanced. Will be balance of work and heat. Okay, temperature of tank varies such a way. Okay, so we have to tell what is the temperature of the tank. Okay, so it shouldn't be a problem. Okay, let's check. So from first law we get that Q is equal to delta U plus W. Okay, now at any state, let me think about it for a moment. Okay, or we can consider it for a small change, so we can write delta Q is equal to du plus delta W. when we like make it delta q, since q1 is constant, we'll get minus k1 delta t, and for du we will get m c dt plus, and for this also work done, also we will get minus k2 dt. Delta t will be similar to dt here because t is a point function. Okay, now what we did get, so wait a minute. Okay, let's remove this first. We can like this is the case for there is some something like at a particular rate the heat is removed, and at a particular rate the work is applied to the system. So if we use the I mean we can definitely use uh, okay, so first thing mistake, that it is rate of work input mentioned here, and similarly it is coil at the rate of, so it's q dot and w dot. Okay, so if we apply first law of thermodynamics, we can get q is equal to delta u plus w. If we like differentiate it with t, okay, so with respect to time, so we get q dot is equal to du by dt plus w. Okay, now we get du by dt is equal to q dot. Q dot we calculated earlier to be minus k1t, and for w dot we get it to be minus of minus, so it should be plus k2t. Okay, now since we get du by dt, you can we can already like calculate, we can always integrate it. Oh, why should I integrate it? So we can write d by dt of, we can write du as mc t, we can write u as mct, and so I can write this as t into k2 minus k1. So from here I can write it as mc dt by dt is equal to t times of k2 minus k1. Okay, now I can like find the solution by integrating it. So I can make it like dt by t mc is equal to t times of, sorry, not t, k2 minus k1 times of dt. Okay, now if we integrate both sides, okay, now if we integrate both sides from so let's integrate both sides. If we integrate both sides from let's say t naught to t, initial temperature is t naught, final temperature from in time 0 to t seconds. Okay, so we will get here mc ln t by t naught is equal to k2 minus k1 into t, and we can further like simplify it as t is equal to t naught into e की power k2 minus k1 upon mc into t. So this is our expression we got. So we can see from here that if k2 is greater than k1, so this should be positive and temperature will increase exponentially. Okay, so we will be moving to the next question now. So let's proceed with the question. A rigid tank is connected through a valve to a steam main supply. Okay, so there is a main supply here. Okay, let's say this is the main supply. Okay, now we have taken a connection from there and we have supplied this connection to a rigid tank. Okay, so since it is a rigid tank, its volume will be constant. Let's make something clear. Since tank is rigid, for rigid tank, volume is equal to constant. Okay, now is connected to valve to a main steam main supply line steam at 1 megapascal 400 degrees Celsius, and HI is equal to 3264.5 kilojoule per kg. The heat is transferred from the tank to the surrounding. Heat is transferred from the tank to the surrounding. Let's say Q amount of heat is equal to 2000 kilojoule. Okay, the energy contained in tank is same as before. Okay, so we can say that T1 will be equal to T2 and it is sent that energy equal, so or U1 equal to U2, U1 equal to U2. Okay, now what more is said? Negative potential mass of the steam that enters the tank. So it is ancient Mi is equal to what will the Mi. Okay, so let's start with the mass balance equation. So we can write from here dm by dt of Cv is equal to m dot I minus m dot E, and from here we can write m2 minus m1 is equal to m dot or not m dot Mi. This is our equation number 1. Okay, now we will move to next equation, that is energy conservation equation. Energy conservation equation represent del U by del T at constant Cv is equal to m dot I Hi plus Q minus m dot E He plus W. This W is 0 and this Me is also 0. No mass is exiting, so we will get U2 minus U1 is equal to so this term should also be 0 because U1 is equal to U2. Okay, now let's continue. Since this term is 0, we can write Mi Hi is equal to minus Q is equal to 2000 kilojoule. Okay, so I can understand it. Mi is equal to this. Okay, so from here I can calculate Mi is equal to 2000 upon Hi. Hi is given as 3264. Let me calculate this value. So what we have to do, 2000 divided by Hi. Hi value is 3264.5. We will obtain the value of Mi to be 0.613 kg. Okay, so this is the answer. Next, if we solve question number 27. Okay, let me do it here. If we do question number 27, we can take like a mass m is of a perfect gas at pressure P1 and volume V1 undergoes an isothermal process. The final pressure P2 V2. The work done in the system is considered positive If R is the gas constant and T is the temperature, then the work done. Okay, so we know that for isothermal, the work done for a uh, gas can be isothermal. For isothermal process, work done for a gas can be done as P1 V1 into ln of P1 by P2. Okay. Now, if we look at the option, or what can we write? P1 V1 ln of V2 by V1. Okay. The work done in the system is considered that then the work done in the process is P1 and V1, and also a similar process, final pressure being P2 and V2. Okay, so P1 V1 V2 by V1. This option is correct. Okay. Now if we look to the other options, so this option is also correct, but mass m here they mentioned, so there should be mass m, and it is so this should also be correct because mrt p2 by p1, because if not for minus sign it should be p1 by p2, but since it is minus sign, both a and d should be correct. Let me verify. Okay, but here, since if you have to only select one option, then you should select this option. And why is it? Because in question it mentioned if R is the gas constant and T is the temperature. So for using R and T, you have to write the option, so you can select the option D. Okay, although both options are correct. Okay, so we will proceed to question number 28. Question number 28, calorically perfect gas. Okay, a specific heat at constant pressure Cp is equal to 1 kilojoule per kg Kelvin, enters and leaves a gas turbine with velocity, same velocity. Okay, it enters a gas turbine. Okay, so let's say this is the gas turbine. It enters and exits same velocity. Okay, so C1 is equal to C2. Okay, and temperature of the gas at turbine entry is equal to 11 so Kelvin, and T2 is equal to 400 Kelvin respectively. The power produced is work output we obtained is 4.6 megawatt. The heat escapes at the rate of 300 kilojoule per second through the turbine casing. Mass flow rate of the gas through the turbine is okay. So we can write the energy equation. So first we can apply steady flow energy equation here. So from steady flow energy equation we can write H1 plus C1 square by 2000 plus GZ1 by 1000 plus Q by m dot. Okay, Q by m dot is equal to H2 plus C2 square by 2000 plus ZZ2 by 1000 plus work output upon m dot. So there will no potential change in the system. C1 is equal to C2, so this will also be reduced to 0. From here we can write H1. So we have to find? We have to find m dot. So we can reduce this equation as H1. A value of H1 will be Cp into T1. T1 is 1100 minus T2. T2 will be our 400, and taking Q by m dot on another side, we can take 1 by m dot common, and we can obtain QW is 4600 kilowatt minus Q dot is in 300, so minus Q's, but Q is already having the negative sign convention because it is acting from the surface. We can calculate m dot is equal to 4900 divided by 700 is equal to 7 kg per second. So option is B. Now we can continue moving to our question number 29. In question number 29, it is mentioned that cylinder contains 10 meter cube of ideal gas at a pressure of 2 bar. This gas is compressed in reversible isothermal process till its pressure reaches 15 bar. What quantum of work will be required for this process? Okay, sure. The work done for the gas will be equal to P1 V1 ln of P1 upon P2. So we have been given P1 is 200 kilopascal, V1 is 10, ln of P1. Value of P1 will be P1 is be 2 bar upon 15 bar. Okay. Now we get the values 2000 ln 2 minus ln 15. Now we have to calculate the value of this. Okay, ln 2 by 15. So ln 2 by 15 can be written as ln 2 minus ln 15. Furthermore, ln 15 can be written as ln 2 minus ln 3 plus ln 5. Okay, so we have the value of ln 2, ln 3, and we have the value of log to the base 10. So to convert it to log to the base, we have to multiply it by 2.30. So we can write it as 2.303 times of log to the base 2 minus log 3 minus log 5. All of these log have base of 10, so we can directly use these values which are given here. So let me calculate the answer. So log of 2 is given as 0.301 minus log of 3 is given as 0.475 minus log of 5 is given as 0.698. So we get the value of this to be minus 0.872, and we will multiply it by 2.303. Okay, so we get this value as minus 2.008, and we can directly use it here. Minus 2.008 into 2000, we get the value as minus 4016 kilojoule. Okay, so it is asked how much work will be required. It means this will be work required will be 4016 kilojoule. So it is be around this answer. Next question. Okay, so in question number 30, we have to calculate the thermal efficiency of this cycle that is shown. So thermal efficiency or performance of the cycle will be given by desired effect upon heat supplied or energy input. Desired effect upon energy input. Okay, and in this case, since it is a cycle, so we can tell that work is equal to cyclic integration of heat. And for the TH diagram, the area inside the curve, area of the cycle is equal to the heat. So if we calculate the area, we can calculate the work done, that will be our desired effect over here. So desired effect is equal to half into base will be 5 minus 1, that is 4, into height will be 700 minus 300, that will be 400. So we will get desired effect to be 800 kilojoule. And for energy input, we can see here that for this process, let's say this 1 2 3 1, the energy input will be from area under this curve 1 to 3. Okay, so this total will be the energy input. And if we consider only this part, So this part will be rejected energy, and that will be rejected from the cycle. We will see it in further details in the next lecture, in that is of second law of thermodynamics. So energy inlet will be half into like area of upper triangle 4 into 400 plus area of this rectangle, that will be 4 into 300. So we get the value of 2000 kilojoule, and so efficiency will be desired effect, that will be 800 divided by 2000, and the efficiency will be 40%, that is 0.4. So option C will be correct for this. Then moving to next question, it is asked an ideal gas at a 20 bar and 40 degrees Celsius is contained in a small cylinder having volume of 15 centimeter cube. Okay, 20 bar 400 degrees Celsius contained in a small cylinder having volume of 15 centimeter cube. This cylinder is placed in a large container having volume of 1500 centimeter cube. The large container is perfectly evacuated and insulated by an appropriate means. The gas is allowed to expand freely and fill the large container. The pressure at the equilibrium condition is. Okay, so we have been given that a small container placed inside a large container. Okay, so let's say this is a large container having the volume of 1500 centimeter cube, and inside it has been placed a smaller container having volume of 15 centimeter cube. Okay, we know that let's say this state 1, this use this state 2 for this condition. For state 1 we have pressure P1 is equal to 20 bar and temperature T1 is equal to 40 degrees Celsius, that is 273 plus 40 will be 313 Kelvin. And volume, of course, volume V1 is given as 15 centimeter cube, that will be, if we convert it into meter cube, so 1 meter will be 100 centimeter, so it will be 15 into 10 power minus 6 meter cube. Okay, next we will be what we will do, it is said that the large container perfectly evacuated, so it was vacuum, there's vacuum in the large container, and it is allowed to expand freely, so the gas is expanding freely, so the net work done will be zero. So it is a case of free expansion here also. Okay, so in case of free expansion, what will happen, since the gas is ideal gas, so the temperature T1 will be equal to T2. Okay, and it is asked what is the pressure at the equilibrium condition. Okay, so to obtain the pressure we can use ideal gas equation, PV is equal to MRT, although we don't know M or M of the mass of the gas or R of the gas, but we can always use PV by T is equal to constant, and we can use all the values here. So let's see, pressure is P1 is 20 bar, V1 is 15 centimeter cube divided by T1 is 313 Kelvin is equal to P2 that we have to calculate into V2 is 1500 and T2 is again 313 because there is it is a case of free expansion. Okay, so we will get our value to be P2 is equal to 0.2 bar. Let me verify the answer first. Okay, so this answer is correct. We will moving to next question, question number 32. In case of question number 32, it is work is done on an adiabatic system. Okay, due to which the velocity changes from 10 meter per second to 20 meter per second, elevation increases by 20 meters and temperature increases by 1 Kelvin. The mass of the system is 10 kg, CV is 100 joule per kg Kelvin, and gravitational acceleration is 10 meter per second square. If there is no change in any other component of the energy of the system, the magnitude of total work done on the system is, we can use the steady flow energy equation here. So we will write H1 plus C1 square by 2 plus GZ1 plus Q is equal to H2 plus, so there is also mass of system. We can directly use Q by M H2 plus C2 square by 2 plus GZ2 plus net work by mass. Okay, now since there is since the system is adiabatic, so Q should be 0, this term would be 0, and it is said that temperature increases by 1 Kelvin. So H2 minus H1, so here we can see that H2 minus H1 will be 1 Kelvin. So we can like transfer the data here. So let's see what has been asked. Since they know the magnitude of total work done, so we have to calculate total work. So total work we can calculate by like calculating all these terms. So let's see what are given here. The velocity change from 10 meter per second to 20 meter per second. Let's talk about H. The temperature increases by 1 Kelvin. It means that H1 minus H2 will be minus 1 Kelvin. Okay, so the Cp is or Cv is 100. So in here what else we can do is we can move work done from that side to this side. Move work done to left side, so we will get minus W by M. Value of M is 10, is equal to H2 minus H1. First term will be H2 minus H1. So H2 minus H1 we have been provided by like value of C is MC delta, so C delta T. So C we have 100 given, into delta T we have provided with 1 plus G times of G, value of G is provided to be 10, and Z2 minus Z1 we have given as 20. Okay, now there is one more term left, that is velocity factor. Okay, so C2 is given as 20, 1 by 2 of 20 square minus 10 square. Okay, so from this we can get our values to be, from work done to be minus 4500 joule. Okay, and we can write it as 4.5 kilojoule. Since it is here it is not asked about what is the magnitude in which direction it wants to work, so we can just so it is mentioned that we just need the magnitude of work, so we can enter the value of 4.5 in kilojoule, since it is mentioned here kilojoule. Okay, let's see question number 33. So in question 33 it is mentioned that the specific heat at constant volume for an ideal gas equation is 2.5 times of universal gas constant. Okay, when the temperature increases by 100 Kelvin, when temperature increases by 100 Kelvin, change in the molar specific enthalpy. Molar specific enthalpy. Okay, so it is asked about molar and specific enthalpy. So specific enthalpy is H, small h. So if we are asked about change, so delta H is given by Cp into delta T. Okay, now we have provided with delta T, we have to calculate Cp. So we know that Cp minus Cv is equal to R. So Cp we can calculate from here to be 3.5 times of R, and delta H will be 3.5 times of R into delta T. Delta T is 100, and we can substitute the value of R to be 8.314, and we will get the value of delta H is 2909.9 joule per mole. Okay, so this is question number 33. Let's move to question number 34. Question number 34 is mentioned that an insulated rigid pressure vessel is divided into two portions by a movable partition. One part of the vessel is okay, so first of all it is insulated. That's insulated. Second, it is rigid. Okay, now it is mentioned that there is a movable partition. Okay, so let's say this is a movable partition. Okay, one part of the vessel is occupied by an ideal gas at a pressure P1, V1, T1, and another part is occupied by the ideal gas at pressure P2, V2, and T2. Okay, now the partition is removed and the two gases are and the two portions mix adiabatically. Show the final pressure P3, the final temperature T3 are given by this. Okay, so in last lecture when I told you about three most important points about adiabatically mixing of the liquid. Okay, so what were those 3 points? So the first is you must use state of the state equation. Okay, that is PV is equal to MRT. Second is you must use conservation of energy, and third is conservation of mass. So these are the basic points which you should know, remember, and always apply in cases of adiabatic mixing. Okay. So now let's start with what we can start with. Let's start with the mass balance, mass conservation. Okay, so we can say that from ideal gas equation we see that PV is equal to MRT, so we get M is equal to PV upon RT. From this applying mass conservation we can say that M1 plus M2 is equal to M3, M mix or M3 we can say after mixing. Let's say that after mixing the system becomes P3, V3, T3. Okay, so we will calculate the required values. So we can say that V3 is equal to V1 plus V2 directly. Okay, now moving to mass term, so we can say that from mass P1 V1 by RT1 plus P2 V2 by RT2 is equal to P3 V3 by RT3. Okay, so from here we can like cross the R values, and what else we can do from here? We can directly remove, like we can calculate T3 value from here. So T3 is equal to P3 V3 upon P3 V3 upon P1 V1 by T1 plus P2 V2 by T2. Okay, now we can we also have to calculate the value of P3 V3. What will the pressure will be required, because we know V3 is equal to V1 plus V2. What we require is what will the pressure P3. So we can also apply conservation of energy. Okay, so since there is no transfer of heat or work inside the system, so internal energy 1 plus internal energy 2 should be equal to, U1 plus U2 should be equal to U3. Okay, so we can write it as MCV. CV is our open CV. We can like cross from all the values. We can write M1 plus T1 plus M2 plus T2 is equal to M3 plus T3. Okay, so from ideal gas equation we can write from here that m into t is equal to pv upon r, or m into t is directly proportional to pv. So we can write it as p1 v1 plus p2 v2 is equal to p3 v3. From here we can obtain p3 is equal to p1 v1 plus p2 v2 upon v3 v1 plus v2. So we have obtained differentiation, and from using this we can calculate t3. We can substitute here t3 is equal to p1 v1 plus p2 v2 upon p1 v1 by t1 plus p2 v2 by t2. Okay, so we have calculated both these equations. So we are done with question number 34. Next, move to question number 35. Okay, so it is mentioned that let's wait for a minute. Okay, so question number 35 is the heat capacity at a constant pressure of a certain system is function of temperature only. Okay, so this is the formula. If T is temperature and system degree Celsius, the system is heated while it is maintained at a pressure of 1 atm. Okay, until the volume increases from 200 centimeter cube to 2000 to 2400 centimeter cube. Its temperature increases from 0 degree Celsius to 100 degree Celsius. Find the magnitude of heat interaction. So we can so since the process is constant pressure process, okay, sorry, it is constant pressure heat capacity. Okay, so here it is mentioned that it maintained at 1 atmosphere. So for constant pressure process, heat, that is asked in question part A, the heat interaction is equal to mcp dt, integration of mcp dt. Okay, or if we want it in per kg term, so we can directly use cp dt, and if we do it, so we have cp is equal to 2.093 plus 41.87 upon t plus 100, okay, times of dt. Okay, so we can now proceed with the integration, and from where to where we have to integrate, from 0 to 100. Okay, now we can write q is equal to 2.093 into t we will get, but for that we, okay, let's write completely, minus plus 41.87 integration of 1 by t, we write it as ln t. So from here we will also write it ln of t plus 100. Okay, now we have lower limit of 0 and upper limit of 100. So after substituting values, we can calculate the heat transfer value. Okay, so let me calculate it first. So ln of from 0 to 100 into 41.87 into ln 2, okay, plus 209.3. So we got the answer as 238.32 kilojoule or joule. This should be joule. Okay, now in next part it is asked how much does the internal energy change of the system increase. Internal energy of the system increase. Okay, so it is asked what is the value of delta U. Okay, so delta U can be written as